I'm pleased to introduce our second speaker for today, Wenqi Jiang, who is a PhD student in Professor Alonso's System Group in the Department of Computer Science at ETH Zurich. And he'll talk about his work on a high-performance FPGA inference engine for recommendation systems.
So thanks, Cathal, for those nice introduction. Okay, so hi everybody. My name is Wenqi, and I'm a PhD student at ETH Zurich. And today I'm happy to present you one of our series of research projects collaborating with Alibaba that actually accelerates real-world recommendation systems on FPGAs. So let's see what we have done here. So personalized recommendations are everywhere, right? So whenever you use e-commercial platforms like Alibaba or Amazon, or you go to video platforms like YouTube or Netflix, or you use social medias like Facebook or Twitter, what those companies does is that they will feed products to you based on your personal preference. And what happens in the data center is that those companies will have a bunch of candidates that you might be interested in. And then for each of the candidates, they will run a machine learning inference on it. And they will score each of the candidate item and only recommend those of the items that has high scores, which means you're likely to click on it. And it turns out that these workloads are very popular in data centers. According to Facebook, almost 80% of the workload in some of their data centers are running this recommendation inference. So it's definitely valuable if we can speed up those inference process. So it's enough for appetizer. Let's jump into the technical part right now. So I'm going to present you this machine learning model first, and then we can look into the hardware part. So similar to any other machine learning model, first you need to have some input feature. And there are two parts of input feature in this model. One is the dense feature. It's the regular features that we will see in any of the machine learning models. And they are fed into some fully connected layers. And the unique part in the recommendation model is that you also have some sparse features. And what are those sparse features? So for example, if I go to YouTube for some videos, I will have a YouTube account ID. Let's say the account ID is 1 million. And our host, Cathal, also have account ID, and his ID is 1,000,001. So although our IDs are very close to each other, it doesn't mean that our preferences are very close to each other. So those IDs are just sparse features that is used to present your ID, but it's not semantically meaningful itself. So what those companies do is that for each of the user ID, they will train a vector called an embedding vector that represents your preference. For example, I may have a 64-dimensional embedding vector that represents the preference of mine. And for each of the sparse feature, the model store all of these features in a big table called embedding table. And the key of the tables is my sparse feature like user ID, and the value of this embedding table is the feature vector that I just introduced. And there are many of those sparse features. And for each sparse feature, you will use your entry ID to do an embedding table lookup operation to retrieve the vector. And you concatenate all of those vectors with your dense input features. And then finally, you feed those features into some fully connected layers. And then you predict the click-through rate, which means how likely the user will click on your contents, and the higher, the better. Now, the problem is that the embedding table lookup is pretty unique in recommendation system, but it's also a problem. It's a bottleneck. Why is that? Because first, there are many of those embedding tables. And in order to access each of them, you need to have one memory access per table. And those are just random access because each of the feature vectors are very short. From our experience, each feature vectors varies from just 4 floating point numbers to up to 32 floating point numbers. So less than 100 bytes, quite a short read. and you need hundreds of those short reads to do the embedding table lookup operation. So from the hardware aspect, that's a problem. Another problem is from the software aspect. Like existing machine learning frameworks like TensorFlow or PyTorch, they're not really optimized for this embedding table lookup operations. In order to do an embedding table lookup, you need to really call a lot of basic operators in TensorFlow or PyTorch. And according to our observation on TensorFlow serving, which is a framework that is already optimized for machine learning inference, it still invokes 37 types of operators just to do this embedding table lookups. And if you have many of those lookup operations, of course, you will call those operators many times. And those are the function call overheads. So now we know that we have the drammaxes overhead, we have the software framework overhead. Let's take a look at the real profiling that we have from the models from Alibaba. So here we have 3 models, real models, and the smallest one is just 1 gigabyte, and the largest one is more than 100 gigabyte. And on the y-axis, we have the normalized latency of the machine learning inference, and the blue part is the embedding table lookup part, and the green part is the fully connected layer computation. And if you look at the number here, actually, most of the time are consumed on the embedding table lookup operations, which might not be the same as you expected, because typically people optimize DN computation because they are the typical bottleneck in other neural networks. And in order to solve this problem, which is the embedding table lookup bottleneck problem, we wrote our first paper, which is called MicroRec. It was published at MLSys last year. And the object of this paper is that we want to develop a high performance and low latency inference engine in order to do real-time recommendation inference. And in order to maximize the performance, of course, we want to eliminate the embedding table lookup bottleneck. And the key idea here are twofold. First, we have a hardware solution based on FPGA to solve the embedding table lookup bottleneck. And the second one is a data structure solution. Basically, we are trying to reduce the number of DRAM access required without modifying the model itself. So on the FPGA part, we use Xilinx U280 Alveo card that is available in our cluster. And if you use FPGA, first of all, you already remove the software framework overhead. So the only thing left is the many DRAM access. And let's take a look at how we speed up it. So U280 has several types of memory. One is the traditional DDR memory, which has a larger capacity FPGA, like 32 gigabytes. So what we can do is that we can store some of the largest embedding tables on the DDR memory. It also has some HBM, high bandwidth memory. So the feature of those high bandwidth memory is that it really has many independent memory channels. There are 32 of those channels, and you can access them in parallel. So what we can do is that we can store some of the medium-sized table into those HBM banks, and we can do the lookup operations in parallel. Apart from that, of course, we also have some on-chip buffers like BRAM and DRAM. So we can store some of the smallest tables in this on-chip buffer. So in this part, the random memory access is almost 0. So we implement embedding table lookup controller that controls 3 types of memory. It will receive the inference request that is sent from CPU, and then it will do the embedding table lookup to all the tables, and then feed the concatenated feature to the DN computation PEs, and then the predicted click-through rate will return to the CPU. Now, the second part is that we also want to reduce the number of DRAM access without changing the model itself. So how can we achieve this? Now, let's take a look at this toy model on the left. So there are 2 tables A and B. And if we use the original lookup method, obviously we need two individual memory access to retrieve, for example, entry A0 and entry B0. But what we can do is that we can also concatenate those entries together, concatenate A0 and B0 into a single longer vector and retrieve it with a single memory access. So you might ask that, what is the point of this operation? Well, remember that each of the feature vectors are very short. So even if we concatenate them together, it's still very short. So reading this longer concatenated version of vectors is also almost single random DRAM access. So when we concatenate them, we almost double the performance. However, if you want to do this, you also need to concatenate all other combinations because you want to look up each of the possible combinations of them. So in this case, memory consumption is an overhead because now the table becomes larger. It looks like a problem. Well, in reality, it is not. So we observe the features of the real world recommendation model. And it turns out that the sizes of those embedding tables are actually quite unbalanced. There are some very small tables just contain 100 entries or so. There are also some very large tables that consumes more than 100 gigabytes just for one single table. So what we can do is that we only apply Cartesian product on those small tables. And this only introduces 2 or 3% of extra memory consumption. And in this case, we can reduce the number of memory access by a lot. Now let's show you some experiment. The FPGA I already introduced. It's Ovio U280, and the CPU is a server that we rent on AWS. But the main point here is that the CPUs and FPGAs are roughly the same expensive if you go for a cloud service. And for the model, we have two models in this case. One is around 50 tables, another is around 100 tables. In the later half of the talk, we will see even larger model, but at this point, it's limited by the memory capacity of an FPGA. So we experiment these two models. So MicroRec is mainly targeting the embedding table lookup. So we do experiments on embedding layer alone to see the speed up of this operation. For CPU, we test different batch sizes. Why? Because we want to do real-time recommendation, and you need to do the trade-off between latency and throughput. So the smaller the batch you use, the lower the latency. However, you will also get lower throughput because you're not fully utilizing SIMD. You're having a lot of function call overhead. So we test a series of batch sizes to give you some impression. And for FPGA, we have two versions. One is just using the HBM and the DDR on-chip memory, purely hardware solution without involving the Cartesian product. And another one is combining the hardware solution with the algorithm solution to show you like how much the algorithm part will help. So let's take a look at the hardware-only solution first. And it's already very impressive. You achieve around 10x speed up on the embedding layer. And if you add also the algorithm solution, it further improves the speed up by 30 to 60%. And you can get almost 15x speed up compared to CPU on the embedding layer. And consider that you only pay 2 or 3% of extra memory for Cartesian product. It's quite worthy to do this operation. And now let's take a look at some real recommendation inference from the embedding layer to the fully connected layers, or finishing the entire inference. And we still test several batch sizes. For FPGA, we test two different precisions, 16-bit fixed point and 32-bit one. And we can achieve around 2.5 to 5.4x speed up compared to CPU. The fully connected layer speed up is not as impressive as the embedding layer because in this specific FPGA model, it still uses DSPs, which is not really optimized for machine learning inference, like later Xilinx model, like Versa, that we can discuss later on. But still, it's quite impressive speed up because the FPGAs and CPUs are more or less the same expensive. So if you have this speed up, you save the proportionally amount of money. So now what we have done is that we know the embedding table lookup is a unique bottleneck in recommendation system, and thus we build MicroRec, which involves hardware and also data structure solutions to solve the problem. However, whenever you build system, whenever you eliminate one major bottleneck, you will soon find another one. So here we have the profiling of MicroRec, and here the red part is the time consumption of the embedding layer, and the rest are just fully connected layer computation. So it actually means that whenever you remove this embedding table lookup bottleneck, the bottleneck shifts back to DN computation again. So we need to solve this if we want to further improve the performance. And another problem, as we mentioned before, is that MicroRec is a single FPGA implementation. It cannot handle really large models more than 100 gigabytes that exist in real industry use cases. So we want to improve this, and we write our second paper called FleetRec, which is published at KDD last year. It not only uses FPGA, it also involves GPU and CPU and group them together into a large cluster to do high performance recommendation inference. So let's take a look. Before I jump into our system design, some introductions of GPUs. Our observation is that GPUs are typically good at regular DNA workflows, but not as good on recommendation. Why? First, like CPU, if you want to do GPU inference, you want to use TensorFlow, PyTorch, etc. And the embedding table lookup involves many machine learning framework operators, which not necessarily friendly to GPUs. Another problem is that GPUs are primarily optimized for throughput. So if you want to achieve high throughput, you kind of need to use very large batch sizes. But for real-time recommendation inference, you really want to optimize the latency. So ultimately, you need to trade off between your throughput and your latency. Another problem is that, like FPGA, you have limited on-device memory. It cannot handle very large models. So our insight is that, can we take advantage of the strength of multiple types of hardware? Not only GPUs, but FPGAs and CPUs. So for GPU, we only wanted to do DNN computation because GPU is almost a matrix multiplication basic. If you have some background of GPUs, for FPGAs, we only wanted to do embedding table lookups because we have such customized and high performance embedding table lookup engine implemented. And GPUs and FPGAs, they have limited memory. And if you want to use those memory to store a very large table, it's very expensive. So we just want to use the CPU's DRAM to hold large embedding tables because they are relatively cost effective. And a naive solution on this is that we can install both FPGAs and GPUs on the same CPU server, but it turns out this is not the best idea. So for example, if you couple one FPGA and one GPU on the same CPU server, you will soon find that one of them might become the bottleneck. Why? Because there are many recommendation models, and some of those models, they have very large fully connected layers, and the computation is really the main bottleneck. Some of them, they have a lot of embedding tables, so the embedding table is more expensive. And if you have deploy multiple models on this fixed ratio setting, you will find either GPUs or FPGAs become the bottleneck. So another problem with this setting is that you need to really specialize your server, install both GPUs and FPGAs on the same server, and it's quite hard to find those servers in the data centers. You need to specialize these servers for recommendation workflows. So our solution here is that we want to connect FPGAs, GPUs, and CPUs by network instead, not install on the same machine. So on the left-hand side, you have some GPU servers, you have some FPGA servers. You can find those servers on existing cloud vendors like AWS, and you connect these devices by network. How do we do that? So for FPGA, we have the Ethernet connection, and we have a TCP/IP network stack developed by our group. So a user can send their inference request to the FPGA, and FPGA do the embedding table lookup operation. They gather the embedding vectors and send the embedding vectors to the host server of the GPU. And the GPU's host server then send the embedding vectors to the GPU by PCIe. So that's basically how it works. So we can still couple one FPGA with one GPU, but the cooler stuff is that we can also do a scale out and mix FPGA, GPUs, and CPUs. So in this case, let's suppose we have a model with very large embedding tables and many embedding tables. So we really need to optimize embedding table lookup layer. And we can have two FPGAs here. And we can also have one CPU, which has vast DRAM capacity to hold large embedding tables. And we group all the three embedding table lookup devices with one GPU. Another thing you can do is that you can do multi-tenant FPGA. So we can split the FPGA in half. Each half serve one individual model. Like on the left-hand side, the model B, we have half of the FPGAs coupled with two GPUs. And on the right-hand side, we have half of the FPGAs coupled with GPUs, one GPU. So it's really flexible how you couple these devices. And if you have idle devices, you can just use them for other workloads. You don't necessarily need them to run recommendation. So really flexible design. And the enabler of this design is the EasyNet, which is the network stack that we developed in the group. Highly recommend you to check it out if you have any network-related applications on FPGA that you want to develop. It supports HIS, and it's very nicely webbed. So it has simple interface with your user kernel. And this is how we develop our engine. So let's take a look at this result. First, of course, we want to focus on throughput, numbers of inference per second. And we still have three models. Here, compared to MicroRec, we have a larger model, which is more than 100 gigabyte, but small and medium models are the same size as the previous one. For the small and medium sized setting, we have compare CPU server, and we also compare FPGA baseline. The FPGA baseline is basically the MicroRec design that we present in the first talk. And we also have FleetRec. We couple one FPGA and one GPU together. And here we can see the speed up. The purple curve is FleetRec and the red curve is the CPU. So we achieve like 50x speed up compared to CPU. And we also have 10x speed up compared to our FPGA baseline. So really the introduction of GPUs fulfills the need of high throughput computation in our case. And for the larger design, we use a more powerful CPU just to make sure you have enough DRAM to hold the model, you have enough CPUs to do the inference. For FleetRec, we also have a larger configuration. We have two FPGAs, one CPU and one GPU. And in this case, you also have 15x speed up. So quite good. In terms of latency, we also have 90% of latency reduction on the small and medium model. On the larger model, we still have 20% of latency reduction, but it's not as impressive as the previous one, because in the larger setting, we involve 4 devices. We have 2 FPGAs, 1 CPU, 1 GPU. So there's some network coordination overhead over there. But still, it's impressive because it still beat the CPU, which only has one server. It does not need to do any communication. So we still beat the single server in terms of latency. And another way to look at the performance is actually the throughput under the latency constraint. So for real-time recommendation. Typically, people can set a latency constraint like 5 milliseconds, 10 milliseconds, 20 milliseconds. Otherwise, when you go to YouTube, you will have to wait 1 minute until YouTube feed any contents to you. So in this case, if we fix the latency to 10 milliseconds, we can see that our solution achieved 40 times to almost 400 times compared to the CPU solution. And if we further reduce the latency requirement, CPU cannot achieve it at all, but our FlickDirect solution can achieve it. Another potential direction is that Xilinx now have this very interesting versatile board, which actually couples FPGA with some AI engines. And those AI engines are just it's an array of CMD cores. So they are really high throughput. It really provides high throughput if you want to do AI inference. Now, what we might improve is that we can couple U280, which has HBM, and also a versatile FPGA for the fully connected layer computation. Now, for versatile, it can provide you really low latency AI inference. For GPU, you still need to do batching. But for versatile, I assume the inference latency is much lower because you can do inference product by product. So that's an interesting direction to go. So to conclude this talk, we present two of the solutions to solve the recommendation inference problem. The first half is the MicroRec, which uses FPGAs that contains HBM and DDR to do high performance and parallel embedding table lookup operation. We also propose a data structure solution using Cartesian product to reduce the DRAM memory access time. And in the second half, we further improve the system design by introducing GPUs and CPUs into the cluster. So the entire system can not only handle high performance embedding lookup, but also high performance computation, as well as being able to serve very large models. And it's also very flexible. You can use existing cloud vendors servers to do this. You don't need any special server configuration for this system. And with this, I'd like to conclude this talk, and thanks for attending, and I'm happy to take your questions.